Okay, so to start the course today, I just want to a little bit reviewing what we have done. Okay. So basically, um, we have dealing with the sum graph, right? Sum graph. Okay. So to check the maximum minimum, okay. If you find any discontinuity, like this whole, okay, then that is not your maximum or minimum point. And when you have the asymptote, also, okay, it will render nearby this asymptote your graph. It might reach an infinite point. It may like this, or just like this. It will stop there and not continuing to crossing the line. And also we have definitions for what is maximum minimum, okay, and what is the absolute max, absolute minimum, local, okay. But the important point, okay, when you are dealing with the functions is finding the critical point, okay, which defined as f prime equaling 0. Okay, that is the first key point for graph. Okay? So if you see this graph, you will notice that at every gradient 0, meaning the gradient is horizontal, okay, the gradient is horizontal, your f prime is 0, and that means that is presumably will be your critical point. And the critical point, it might be maximum or minimum, or it can be not maximum and not minimum. Okay, it's just a critical point. So it's not necessary to be max or minimum. As long as your f prime is 0, then it is fit with the definitions. Like this point here, the corner pointy, this is also maximum, or we can also have like minimum like this. But in this case, because at the corner, you will not have any differentiation, right? Anyone know why? Why we don't have any, why this point, okay, this pointy here is not differentiable? Anyone guessing why we cannot derive at this point? Anyone know? Or maybe guessing why we cannot derive at that point? Okay, so to approach with that question, that's actually really a concept question. Okay, so remember, okay, uh, the f prime definition is the gradient, right? This the slope, right? So you have the slope here, and it is changing, right? It's changing until the maximum. It's horizontal. It's 0, and then it's going down, right? So you have, okay, at the left one, it's going up. At the right one, also going up, and it will meet at exactly one point where the tangent line is 0, right? Okay. But here, what is happening here? When you go here, the gradient is positive, right? You go here, gradient and negative. But what about this exact point, the corner? We cannot define, right? We cannot define with the tangent line. In here, we can define based on our limit approach, okay? Based on our continuity limit approach, we can define that, okay, at that point, our gradient is 0. But this point, because it's pointy, we cannot define whether it is going up or going down. It can be both at the same time. That's why this corner is not differentiable. Okay. Okay. That's just some small review. Okay. And also, this point is also important. It's also gradient is 0. Okay. But it is not maximum and not minimum. It's just a gradient 0. And we can also say this is our critical point. Uh, we can have some sections related to why this happened. Okay, let's start with the let's say we just have our let's say our simple x squared. Okay? Because it's only a quadratic x squared. When you derive, it's just a linear function, right? It's easy to derive. And you look at uh, maybe like that. And I will write this as the f prime x equal to x. Okay. And let's derive one more. If you derive the linear, it will be a constant, right? Constant with 2. Let's say 2 is here. Uh, let's say that is our 2. So let's say this is f double prime, and it's equal to. Okay. Because it's such a simple function x squared, we know that we can derive become linear and become a constant when you derive twice. Okay. In physics, usually it will be related to the easy way to make a visual approach with this is with position. This is position, and this will be the velocity, okay. And this will be your acceleration. So the meaning is, uh, if you're having a movement, someone moves in functions using quadratic formula, meaning he will move with some velocity, and the velocity will change accordingly to this acceleration, the constant acceleration. But sometimes we also see the acceleration also changing, right? I think in physics you call that jerk. I forget the name. I think jerk. It's not the cursing word jerk, but we say the derivative of acceleration. Sometimes people call jerk. Okay. Okay. Let's see the next case. Let's say now you have let's say this is the x cube. Okay. How do we determine the f prime from that from this graph? Okay. Imagine the functions, you don't know the real functions. Imagine you just know the graph. Okay. How you derive the drawing from just this function. Okay. Can you try make your own graph from the functions? Okay. Which means you don't necessarily derive the functions and then draw from the new functions. Try draw the f prime from looking at this graph. Okay. Okay. The idea, okay, I said before, in every graph in calculus, especially in this chapter, the idea is to look at the f prime equals 0. F prime equals 0. So when f prime equals 0, your point is at just 0, right? And see before 0 and after 0. What is happening in gradient? Okay? Because f prime, again, I will tell you, I will brainwash you, I'll make a brainwash. F prime is a gradient. Okay, so everything that changed here is all positive, right? The gradient is positive here. Okay, and then it reaches 0. Okay, but what is happening after 0? It's still positive, right? It's still positive. Okay, so my suggestions. Okay, so if this is f prime, always notice that the part above x-axis marked as positive, the part below marks as negative. Okay, and then we see from these original functions, this gradient is going up, right? It's positive, it's increasing, and then at this point it's 0, and then it's keeping increasing, right? So think and imagine any graph that will be from positive signs, reaching 0 at 0, and then going still positive. So you're reaching at 0 here, okay, at this point. But you will go from positive, right? Positive. So you're going from here, from up, and then reach 0, and then back to positive. Okay? That's the first concept. And if you master this concept, if you already having this knowledge, you will get this. You will get a lot. Like if I give you any graph, any random graph, and I ask you to please check the graph for the derivatives and maybe second derivative, what will happen? Okay. So we can see. So I can draw this from positive to 0 and then back to positive. Okay. And as our predictions, we will see that, okay, this is based on the quadratic. So it will look like a quadratic. Okay. It looks like an x squared, but multiplied by 3. Okay. Okay. Now let's say we need to derive once more. So let's say we need to derive the second derivative. What is happening here? So the same principles, okay, the same principles. What you need to do is finding the 0, 1, the, the derivative that is 0, which is here, the horizontal gradient, and see before and after. Before it's going down, right? And it's going up, okay? So you see this is going down. I will mark this as negative, and this is 0. It's going down, the gradient is changing, and it's going up here. Okay. The same principles. This will be positive, this will be negative. Okay. So at this side, you will move from negative sign. So maybe around here. Okay. This is negative. Okay. And then you'll reach 0. So you move your line, reaching this point, and then it's going up. So it's going up. But because we know also the graph will have a linear function. So it's just a straight line. Okay. And we can say that this is our f prime. It's 6x. Maybe we need to have more lean towards y, but let's just say this is 6x. Okay. Okay. Now back to our original functions. Okay. So this f prime 0, I said before, we can say that it's critical point, but we cannot say that this is max or min, right? But when we derive twice, okay, we derive twice, it will be like this. Or if you see the f prime, the f double prime 0 is changing something from negative to positive. Okay, this is what we call, okay, what we call uh, concavity. Okay, concavity, it has two. It has concavity upwards. It has concavity downwards. Okay. So when f double prime is 0 and it's changing negative, positive, or positive to negative, meaning the concavity changes. Okay. What is concavity? Let's see our original graph here. Concavity. Well, let me draw the upwards first. So concavity upwards is like this. Concavity downwards is like this. Okay. Let's see here. Uh, in this case, actually, these two line here, or this curve, is basically a two concavity in one curve. Okay, we can say that this is having another half, right? If you see the whole picture, it's actually half of this, right? We say this is downwards, and after the 0, it's going upwards. So at this 0 point, concavity change. Okay. And we will know the change from the f double prime. Okay? So let me draw here. So if you see here, this is f double prime equals 0. So at this point, if you see from the graph, it changed from negative to positive. Okay. So you will have when f double prime greater 0, f double prime less than 0. Okay. So f double prime greater 0, you say it's upwards. Okay. It's positive. Okay. When you say downwards, mean it's less than 0. It has negative. Okay. If you see the picture, we bring back the original picture. So it will changing the downwards and then upwards. Okay. Okay. Got it? Got it? Let me give you a few examples how you are using the concavity. Okay, any questions first? Any questions? No? Okay, example. Let's say the functions x cubed minus x squared find max, minimum, and check the concavity. And roughly sketch the graph based on those information. Okay. Okay. I will start just with looking at the simple polynomial functions, x cubed minus x squared. Okay. Easy to derive, right? So I think it will be easy also to analyze and see what I mean with the maximum, minimum, and concavity. Okay. So if the functions do not have any interval, if you look at the some special point, the maximum, the minimum, how they change, outside of that point, this function will be just going down to infinity and going up to infinity, right? If you imagine. So if you imagine like you found some special point, and outside that special point, your graph will go to infinite point. So that means all your max and minimum, you just need to just saying that, okay, this is just a local max, local min. But just saying only maximum or minimum, that's also fine. Okay? Because the question is not really saying or making any difference between the absolute or local. So just saying maximum minimum is fine. Okay, so let's start. Just derive the function first. Okay, derive the functions, and we will have this, and derive twice, and we will have this functions. Okay, we'll have at least two functions. And because it's just a simple function, we don't really much care about any domain asymptote because there's none. And we can just focus on the first derivative and second derivative. So first, making the first derivative is 0. We need to check the critical point that we have. Okay. So 3x squared minus 2x is 0. So I will have at least two critical points from here. X is 0 and x is 2/3. You can check the original value. Okay, this is just 0 and f 2/3. I think it's some number here. You can check by yourself if you want, but I just want to show you just the x. Okay, and then the y double prime, making y double prime is 0. This is to check the concavity. Okay, so this is we call the right side is the first derivative test. It's for checking critical point. And the y double prime 0 is checking the second derivative test, checking the concavity. And we can check the critical point. We can check through the line number like that. And we have 0 and 2/3. So checking the critical point, we check whether it's maximum and minimum. So first we need to check the sign. So checking nearby 0, maybe -1, -1, 3, -3, -2, -5, but it's negative. It's positive, right? It's positive here. Zero and 2/3, maybe 1/3. 1/3, it's 1. Minus, it's minus. And then checking 1 is just positive. Okay, so our graph will be, it's positive, so it's increasing, and then decreasing, and then increasing. So this will be maximum, this will be minimum. So this will be max, this will be min. And checking also the second derivative test. So this is second derivative test. So it's only having 1 point. So we just checking 0, it's negative. Checking 1, it's positive. So negative to positive. So negative means it's less than 0, meaning I will write this is C and D. It's concave downwards, okay? And this is concave upwards. So it will be like that and like that. So it will be downwards and upwards, okay? So you will have a function, the functions. If you want to make some point, so this is 0. Let's say this is This is 1. This is 1/3. This is 2/3. So based on our observations, okay, this will be maximum and minimum. So maybe this will be like that, and maybe going here, it's changing the concavity. So it will be yeah, probably like that. Should be it's going still going up, still going down. Okay. I will give you maybe the what is the functions mean. Yeah, it should be like this. Okay. So at this 1/3, it's changing the concavity. So when we want to go here, it changes to upwards. Okay. So probably I didn't make it really similar because I didn't count the fx. Okay. So you can check your check the f0 and f2/3 and also checking the f, okay, to make sure that this is correct. Okay. But the correct one is like this. So it's going up, it's maximum here, and it's going down. But then at some point nearby this half, 1/3, it's starting to having change in concavity. Okay. Okay. A good idea for the AC. Okay. Any questions first? Yes. What do you mean? Yeah. Um, do you see the concavity changes here? Okay. So it's actually changed around here, right? It's around what we calculate. It's 1/3. Okay. This become the maximum, and this become our minimum, right? It's around 2/3 here, 0.6 something here, right? So let me mark some points here. So this is the 0. Um, maybe around here is 1/3, and maybe around here is 2/3. Okay. Okay. So if you want to make really close graph to the real one, you can check the 1/3 and 2/3 and check the function's value, how much the value is, and then you can make closer to the real one. Okay. Okay. Um, is, is that answering your questions? Okay. But of course, this is the just a simple polynomial function, right? I give this example just to having you get the idea how to solve all the first derivative and second derivative. Okay. I will go back to how we solve if we have, for example, rational functions and any complicated one. Okay. But let's go back to our graph. Okay. Any more questions? Any questions? Okay, let me back to the graph and see if you can handle. Um, have you have I give have I give you this graph? No, right? Okay, so this is just a function. Try to find the first derivative of this function. Uh, Actually, try to draw the first derivative graph from this f. Okay, so uh, if you see any graph in your maybe textbook, you can assume and predict what will happen to the f prime and maybe f double prime. Okay? But let's just check the f prime from this graph. Okay, so uh, maybe I draw it to. So it starts with the just a constant and then smooth curve going up and going down and then going up and then the curve become a constant once more. Okay, so at the beginning and at the end, the curve is like a constant. Okay. I'm not sure if we can make functions like this. This is just just my random makeup function. Okay. Okay. Yeah. But if I give you 5 minutes, can you solve this one? Yeah. No. Okay. For like for. Yeah. Yeah. Sure. Yeah. This one. Okay. To draw the graph, uh, you need to check first finding where the f prime is 0. Okay. That's the first thing you can do. So this is the f prime 0 here, and this also 0. Okay. And this also 0. And this is also 0. Okay. So based on these four key points where f prime is 0, meaning when you draw the f prime x, you will have all these 4 points in 0 position. Okay. Okay, so let's start to try to draw. So start with the let me so maybe around here. Okay, let's say at -2 is still 0. So we have 0 up until maybe -2, and then see the gradient is going up, it's positive, okay? And then negative, still negative, and then change to positive, and then 0. So because in -2, it will be in positive. So from 0, you need to go up, okay? And then reaching some point, and at -1, you need to go down. So from going up and then down. Yeah, maybe around that. Okay. And then it's still going down all the way until you get 1. So maybe my assumption is it's still going down and then having a minimum point there and going up until 1. And then it's still going up. Okay? So this is, remember, it's positive and negative. Okay? And after 1 is still positive until 3. So going up and 3. Okay? And it will stay 0. Okay, so because we have learned the concavity change, right? If we see the original graph, probably we can see that the concavity will change from around this 0 here, concavity change, and this also changed at x equal to. It's changed from this to that. Okay, but also at the first -2 and the last one 3, we can say that especially in -2, not -3, not 3, but at -2, you can say also, because if you try to imagine the curve, when the curve having maximum and it's going down, actually it's want to go up, but it stays 0. We can also say this is inflection point. Okay. So we can check from here. It's actually this is 0. This is 0. And this is 0. This is also 0. But let's just take some observations at this middle one. Okay. So this is where your concavity changing exactly from the graph. Hmm? Let's say it's a smooth, like a smooth. Yeah, smooth. Let's say just smooth. But if this is a corner, then you can make hole. Yeah. Okay. Yeah. But actually, it depends on the graph. Okay, it depends on the graph. But in this case, let's just assume a smooth. I will having an example also for the corner. Okay, what we can do for the corner. Okay. So maybe we can start with this one. Okay. So let's say this f of this function, the functions is the absolute value x. Okay. So what is the graphing for? So actually, you can derive the absolute value, but it will have some exception in the graph. Okay. So absolute value, if you draw, you will have a straight line because it's just actually x. Okay. If you just have y equal x, it's just divide this, right? But if you have absolute value, all the negative number will be positive, and it should be like that. Okay. But because it's linear, it won't have any curve at this point, okay, at the zero. It won't have any corner. It won't have any a smooth curve, so it will have a corner. Okay. So back to the definitions. Okay. So if I'm asking, okay, is this function the absolute value of x is continue or not? Is continue or not? What do you say? Is it continuous function? Is it continuous function? Who say it's continue? Who say it's continue? Who says it's not continuous function? Not continue? Not continue? Not continue? Why it's not continue? Why it's not continue? Okay, this is a very basic concept in calculus. Continuous and differentiable. Okay, it seems similar, but it's different. Okay, okay. So continuity. Okay, always remember. Okay, so all the continuity you can check with limit. Left hand limit, right hand limit. It should be the same when you plug in the number to the function. Okay, so I will write definition so that you will not forget what it's meant. Oh, sorry. So limit as x approach a from positive as fx, it should be the same as limit as x approaching a from the left side. Uh, move here. Okay. It should be the same as fa. Okay. So this is the definitions for the continuity. Okay. Let's say it's the same as L, okay. Any constant L. Okay. So first, check the left hand, right hand limit. Check the function itself, plug in A. It should be the same as L. Or if you imagine, you're writing uh, the curve. You draw the curve. When you draw the curve, if you do not pick up your hand, meaning you will have a continuous, right? It will continue. But when you have, okay, I'm picking up my hand and I continue, it will have a hole, right? Or maybe some jump, okay? So in another way, if I can draw this absolute value of x without picking up my pen, then it's continue. The easiest way to illustrate, okay? because I can draw these functions, okay, these absolute functions without picking up my hand, then I will say this function is continuous. Or if you want to make some mathematical notes, you can prove with this. Okay, you can approach from right, from left, substitute the a, it should be equal with some value. Okay, that's continuous. Every continuous function, every continuous function is not always differentiable. That's the exception. But every differentiable function should be continuous. Get it? Get it? Okay. So if you say any continuous functions, it might have, or it might have not be differentiated. Like this absolute value at the zero, like I said before, every pointy, because you have, okay, approach from left side, approach from right side. Okay, here is, okay, I'm going down, negative, right? And this is going up, right? It's positive. But what we can define at this point, we cannot define, right? Whether it will it be negative or will it be positive? It's strange, right? So because it's strange, we cannot define at exact point here. Okay, that's why we still can differentiate the absolute value, but with some exception, okay? With some exception. So the derivative of x is just 1, right? So it's just a value. So let's say we have 1 here, we have negative 1 here. So our definition will be based on our definition. This is our derivative. Okay? Just a constant value with a whole. Meaning the whole meaning, the functions is actually not differentiable at x equals 0. Okay? Based on our definition of continuous and differentiable. Okay? Okay? Well, let's try this one. I already marked the f prime 0 for you. Okay, so now we have in -2, you have a pointy. In -1, also you have not a smooth curve. In one, no, in yeah, in one also it's having a pointy. Let's say this one here is vertical to this point. Okay, so it's exactly going down here and reaching 1. Because again, this is a make up functions, just random functions. So try your best to graph the first derivative. If it is in exam, I will make real functions. Okay, real functions. I mean, we can prove with the graph. This is I cannot prove with the formula. But try to illustrate and have a predictions for the F prime. Okay. Now we have at least four points for the F prime to be 0. Okay. Let's see from here 0 is positive, and then 0, and then it's all negative. Okay. And then it's positive, and it's negative. So we have zeros, at least 4 0. Let's say we have okay. So from the left side of -2, it's still having 0. Okay. But it's pointy, right? So I need to have a hole here. And don't forget, this is positive, this is negative. So I have a hole in -2, hole, and then it's positive, but it's linear. This is linear. So I will have from maybe the positive side is here, right? This is the positive sign. So maybe from here I would also have constant. So it will be having a constant until some point here, and it's pointy one more time, and it will be 0, also pointy here, and going until around 1, and then still it's let's say it's pointy, that pointy like that, and then see that at x equal to it's 0. So this is 2. So because it's this is negative, so I need to have to start the negative one from here. Okay. So maybe it will start from below, and I will need to go up, reaching 0. Okay, reaching 0, and then still going up until I go to yeah, and it's still going down. And also, okay, and also, you can check. I think from this the right side of the graph, we can see that at x equal 3, you see here it's 0, right? So it means this is the concavity change, okay, from positive to negative. So we can say this is our inflection point. Okay. Just to add some notes there. Meaning this is the inflection point. Okay. Okay. We still have around 30 minutes left for our course. I will move on to how to sketch a graph. Okay. I will skip some parts, but I will just giving you the essential points what you need to do if you need to sketch a graph. Okay. So from here, is there any questions from here? Is there any questions? Okay. Notice that this is just a makeup function. Okay. So if you see any weird or maybe some impossible to line, yeah, just make it simple. Okay. As long as you can at least predict how the graph will looks like. Okay. Okay. Let's move on. Okay. This is notes, a summary notes for the whole chapter 4 actually, for the whole chapter 4. Okay. Aside from the mean value theorem. So this is include the extreme value theorem, the second derivative test. Okay. So first, let me explain the first thing when you try to do the sketching for any curve in calculus. Okay. Always remember the domain. Okay. Always remember the domain. The possibility of x. Okay. Can your x uh, plug in into the function? If this is possible, then that's not a problem. But if there is any exception, for example, like 1 over x, x should not be 0. So 0 is your probably asymptote, right? Probably asymptote. But in the domain case, 0 should not be included, okay, to make the functions continuous. Okay, so domain. And then the second one is the intercept, okay? Uh, is there any intercept for the curve? Finding the intercept, x-axis, y-axis, finding when they crossing the axis. Okay? And then symmetry, odd functions, even functions. Have I told you the even and odd functions? Not yet. Have I told before? Even and odd functions. Have I told before? Even and odd. No, right? No. Okay. Okay. So odd and even. Okay. If you remember our graph, this x cube. Okay. Remember our old friend x squared. Okay. We say the right one is symmetrical. Okay. You can mirror left, right. Okay. The cube is asymmetric because you cannot mirror left, right. Okay. So every time you have an odd function, it will be asymmetric. So this will be even will be symmetric. Symmetric. This is asymmetric. And how to prove? Okay. How to prove? You need to check the negative x. So you put in negative x inside your function. If it is the same as your old functions, then it's even. If it is negative, then it's odd. Okay. So this is even. This is odd. Okay. Even and odd. And then asymptotes. Okay. Asymptotes. We need to bring back our limit. Okay. So if when you have x approaching infinity in your limit uh, of your functions, if it is reaching some number, okay, then that is your horizontal asymptote. Okay. So it will be, let's say, we have like that, and yeah, the red line is your asymptote. This is your graph. Okay, so your graph will not crossing the asymptote. Okay, will not reach the asymptote. So that's horizontal asymptote. Or you have the vertical asymptote. Okay, limit approaching a. This means negative and positive means it can be left or right. Okay, it will have infinity or negative infinity. It will have a vertical asymptote. maybe like that. Maybe it's going up like that. And then after dealing with the asymptote, okay, you're dealing with the first interval, the first derivative. Okay, you check whether the function is increasing or decreasing. Okay? So this is the f prime test. Okay? You also check the critical point, okay, to find maybe it has the maximum minimum. Check the critical numbers, check critical points, check whether it is minimum or maximum. So that is the first derivative test, and then the second one is the second derivative test. Okay? So you check the concavity, check the inflection point. So this is okay, and with all this information, with all of these informations, then you can sketch the graph uh, without making any, like you are minimizing your mistake to sketch the graph based on all of this information. Okay. Okay, any questions? Any questions? Basically, that is all for chapter 4. Besides the mean value theorem, and we have optimizations, but it will be later. Okay, any questions? Any questions? Okay, so I hope you can understand at least the logic, okay? At least the logic how to sketch a graph, okay? Because it is really um, making sense to your math concept. Like you need to know the domain first. That's why at the first chapters I will always tell you, okay, how to find the domain, how to find domain. But still, some of you are making mistake to find domain. Okay, that's the very basic concept of math. Okay, that's very basic. Please remember how to find domain. Okay, domain asymptotes. We deal the asymptotes. We are dealing with the asymptotes at the very, I think, early chapters in limit. Okay, in limit we have uh, when limit reaching the infinity and infinite limit, we dealing with the asymptote, and then we are dealing the derivative. Okay, the derivative. We say that when the function increasing, decreasing, the tangent line is changing, etc. Maximum, minimum, dealing with the critical number, but max and min and the f prime is all one package in derivative, right? One package in derivative. And this is just an additional note for the f prime. You can also check the f double prime to check the concavity. When the graph change its concavity, okay? Like from the upwards to downwards, or from downwards to upwards. Okay. 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 Um, I will give you example. Maybe just giving you um, a questions that can you solve these questions? Okay. 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 Try for several minutes, or maybe I can give you maybe 5 to 7 minutes. Okay. See if you can solve it. Uh, if you finish solving this graph, uh, maybe I will give you a bonus point. Okay, can you try? At least the graph doesn't need to be really perfect. Okay, doesn't need to be really perfect. At least the characteristic of the graph based on the calculus uh, is it can be observed from your graph. Okay? That's good enough to draw. And for next Monday, because I moved the schedule for the quiz to Friday. For Monday, we can have, so I will have the course for chapter 4, and then we can have also some review for your quiz. Okay. Okay, if you're dealing with these functions, because we need to find the first derivative, second derivative, I hope you can derive this. I hope you can derive this. If you're still having difficulty to derive this, uh, I'm not sure how to help you. Okay, I'm not sure how. You need to have time dealing with the concept. Okay. Do you get it? Do you understand this? From mm-hmm. Huh? Uh, yeah, you can solve this. You can like, but I think this this is maybe some calculations. You need to check your calculations here. Yeah, I think you need to use the quotient rule, F over G. Yeah. If you have having difficulty to derive this, this you can derive through your F over G situation of the quotient rule. Okay. But maybe before you derive, you can check the domain, check the asymptote, whether it has asymptote. Do you get the solution for last time? The x6 plus y6 equal 1? Uh, I get it, but you need to actually, there are some form in the solution that is will bring back x6 plus y6, and that you can rewrite into just 1. and you will have the 5 over something. Mhm.